Now that Coviscan is available to the public, it is important that the system is reliable and provides a good experience to all of its users. This presentation will cover our motivation for changes, our alternatives, our chosen solution, self-healing stages, architecture before and after, effects of enhancement, testing, concurrency, and lessons learned.
Welcome to Coviscan's second prototype. Here we have our new dark mode, and I'll be demonstrating the self-healing loop, specifically the logging and the analysis portions of it. And just to demonstrate, I have the console open, and I changed the province, and you can see here Coviscan functioning normally. If I open up one of these logs, you can see that we logged the code, the function, the message, the timestamp, and the log type. So one thing we can do is to inject a fault, and this will simulate a network error. So if I do that now, change the province, you can see a bunch of errors have come up. And our logging service successfully caught the error and logged it here. This is code 0, function, message, which in this case is network error, and a timestamp. And just to demonstrate that we can turn off the injection fault, you can see that it's now again functioning normally. So to demonstrate how this enhancement works, we'll first start talking about the motivation behind it.
The motivation for our enhancement was to achieve zero downtime. This can be done by incorporating a self-healing loop into the existing system. The enhancement will improve reliability. This improves user satisfaction. For the dev team, this will improve the robustness of our software. This will also reduce maintenance overhead. Here is a list of some of the options we went through. Firebase Platform handles redundancy and load balancing. Firebase Cloud Functions require zero maintenance. Computing resources are automatically scaled up to match usage. As for Firestore, redundancy is handled through different replication mechanisms. The remaining issue is errors within the Coviscan code base. The next option was to have on-call developers. This separate team would monitor the system and repair for failures. This would most likely be outsourced to a third-party service. The opportunity cost of this is high. This is because of Coviscan's small project size and better uses of an equivalent money cost. Another option is integrated self-healing. With this option, we'll be creating a Coviscan-specific self-managing system. This will be built in-house by Coviscan devs. There will be significant overhead, but the system will be autonomous. This gives the dev team a better view of the system as well as implementation flexibility. For our final solution, we decide to go with integrated self-healing. This is because the benefits of having this system is both cost-effective and feasible for our team. With this solution, we'll be able to cover the areas that Firebase does not support. We won't have to rely on another team, and our money cost is lower.
The architecture, design, and implementation of Coviscan are extended to incorporate self-healing capabilities, with the goal of achieving zero downtime. The ability of our application to support self-management fulfills the DevOps' team need to manage the application. The self-healing loop itself is made up of components which correspond to 4 steps: monitoring, analyzing, planning, and execution. Although, for the prototype, only the monitoring and analysis components are implemented. The first step of the self-healing loop is to monitor the application through logging. By logging the components of our application with timestamps, status codes, messages, and function names, we obtain detailed data which can be analyzed and acted upon. Our approach to logging includes setting up a Firebase endpoint to obtain logging information from Coviscan's front end. This ensures that the system is continuously monitored. The logs themselves are stored on an external server, MongoDB, to ensure that monitoring can occur even if Firebase is down. And these logs are leveraged by the analysis component. The analysis service determines if components are working normally and reports behavior that is indicative of a failure. Expected behavior of the system is determined by metrics such as frequency, count of error codes, severity of issues, and the number of concurrent users. If these values are exceeded, then a failure has been detected. The component is hosted on Mongo Realms, a separate platform from Firebase. This is done to avoid disruptions in logging if Firebase fails. It works off of database triggers and executes every time a front-end log is posted to the database. From there onward, using the logging info, it either stores the log as an error in a separate collection or updates the counter to keep track of operation and performance metrics. While actions or mitigations aren't implemented in this prototype, the foundations are laid, and there are a few mitigation options that are plausible for future enhancements. One strategy is to retry after failure. If a function does not execute the first time, a retry tactic can be implemented in the front end through Axios calls. Another strategy is failover. A failover tactic can be a redirection to another instance of Coviscan if an instance cannot be reached. Then there's load smoothing. Firebase includes load balancing. However, to maintain fast response times during sudden spikes in traffic, Coviscan's functions can be placed in a buffer. This would increase average responsiveness during high loads. Finally, the last strategy is to degrade gracefully. Google Maps and Google Charts are heavily relied upon for the visualization component of Coviscan. Should either of these services become inoperable, a reduced functionality version of the data can be displayed. Since Coviscan provides essential information, a graceful fallback would be to display the data in a text format along with a notification that the visualization system is currently unavailable.
Once a failure is discovered, planning and execution are taken to restore the system to its functional state. The relevant mitigation strategy is chosen based on the results of the analysis. Our self-healing loop would choose a strategy that can contain multiple mitigation tactics to resolve the failure. Since multiple mitigation tactics can be taken, the sequence that the actions are applied may be important. In the final step, the mitigation tactic is executed. This can be achieved through simple scripts or more complicated processes such as bots. Should Coviscan be improved in the future, mitigation strategies should be executed by following this procedure. A log passes through the analyzer and a mitigation strategy is chosen. The analyzer sends a request to the service responsible for executing this strategy. This will all be handled through the analyzer trigger. Pre-enhancement. Coviscan is built following two architecture designs: 3-tier client-server design and model view controller design. The client-server relationship is carried out by the user and their browser acting as the client, and Firebase is acting as the server. The model view controller style is integrated naturally on top of the client-server setup. The view can be explained as a React-built UI that the user sees and interacts with. The controller encompasses all input taken from the user by the React UI. And finally, the server-side components act as the model. Post-enhancement. The existing architecture is augmented by the analysis and logging services discussed earlier. With respect to the client-server architecture, the new services reside on the server side of the system. The complexity of the enhancement would be greatly increased if these services are running on the individual clients. Leveraging the client-server architecture by centralizing the new services greatly simplifies our design. The model view controller has effectively not changed on a high level. Our existing view components allow a DevOps to view the logs and inject a fault to test the logging and analysis services. These new services are separate from the existing services, and they augment the existing architecture by adding the publish-subscribe architecture style to our system. The analyzer, or trigger, is a new service which adheres to the publish-subscribe architecture style. The system architecture has changed due to the enhancement. Even though it consists mainly of the client-server and model view controller styles, the augmented architecture is important to note as the potential features developed in conjunction with the analyzer must now consider the publish-subscribe architecture. For example, features dependent on logs which are improperly implemented by not being subscribed to the database will not function as intended.
Next, the effects of the enhancement with respect to software quality attributes will be discussed. Overall, the enhancement increases the maintainability of Coviscan. We see this improvement because it decreases the amount of work necessary to restore the system from a failure. Additionally, the information provided by the logging and analytics service is valuable for debugging software issues over the lifetime of the application. Evolvability. When implementing new features for Coviscan, the self-healing loop would require additional time and effort to remain as an effective subsystem. At first, this seems detrimental, as each new feature would be required to log data, and the analyzer and mitigation subsystems would have to be improved or expanded to accommodate the new feature. However, the evolvability of the system is improved, as it would ensure the stability of both pre-existing and new features. Overall, the oversight provided by the self-healing loop surpasses the overhead in expanding the self-healing loop. The testability of the system is improved because the act of performing logging and analytics provides effective tools to use during the debugging process. Specifically, effective logs decrease the overhead during the debugging process, and when combined with proper context, drastically improve the ability to identify and locate bugs. Furthermore, logs generated in the backend can be used to identify issues regarding the misconfiguration of databases. Finally, logging can also be used to inform the developers of unexpected, important, or notary events taking place across the entire system. Performance of the front end should not be impacted, as the log requests are asynchronous and happen in the background. Conversely, the logging database, MongoDB, may experience a significant amount of incoming queries when Coviscan experiences a high load of users. Fortunately, MongoDB can support up to 30,000 requests per second. A typical use case scenario for a user involves approximately 10 logging requests. Therefore, without expanding the logging database, Coviscan should be able to handle up to 3,000 concurrent users without performance impacts. Overall, negative performance impacts of the enhancement will be marginal or non-existent. Users should expect to have the same fast and responsive experience as that of the pre-enhancement application. The security of Coviscan is enhanced with the addition of the self-healing loop. Although the enhancement does not directly prevent malicious attacks such as distributed denial of service attacks, the effects of such an attack are mitigated through load balancing and graceful failures of our services. Coviscan's logs are stored on MongoDB. The possibility of the logs being compromised has been addressed in the following way. MongoDB requires a connection string in order to execute CRUD operations on its databases. This is only available to the development team, therefore unauthorized users cannot access the logs. In production, this is encapsulated by environment variables. Moreover, we have also chosen not to expose the Mongo database collections. These measures are taken with MongoDB to ensure that our users' data will remain secure and decrease the risk of vulnerabilities being discovered. Additionally, the logs do not contain personally identifiable information. The system does not store or handle any personal information. Logs only contain metadata that is related to the system code and subsystem interaction messages.
Fault injection within the scope of the Coviscan project is done by intentionally placing a broken endpoint in the application's API calls. Behind the curtains, Coviscan makes up to 4 separate API calls to populate the visualization data. The calls go through an internal API gateway where each visualization element visits a different endpoint. When fault injection is active, the API gateway is replaced with an invalid URL. As such, none of the API calls needed to populate the application returns a 200 code, or successful, and this breaks with several network unreachable errors. The logging and analysis services will then monitor the system for issues. Logs may be sent concurrently through multiple clients running Coviscan. The analyzer must deal with said concurrent logs. Through the utilization of MongoDB's trigger functions, the analyzer maintains a queue of logs which need to be processed and executed sequentially. MongoDB's automatic handling of sequential queuing means that the logging and analysis services have the capacity to handle Coviscan's growing user base. Over the life cycle of this project and this particular assignment milestone, we've learned a few key lessons. One of them being logging as an important feature and should be implemented even in applications without a self-healing loop. Next, a PAS such as Firebase is a great way for smaller teams which have shorter timelines to come up with a minimum viable product. Finally, architecture defines a large system and its interactions. It cannot be set in stone. As applications get new feature requests, it is often found that the architecture may need to be reworked. In conclusion, the architecture was revisited and developed, several new components were added, and the front end received a new function. In the future, a possible direction would be to implement redundancy for all components, perhaps multiple instances managed by something like Docker or Kubernetes.